Good afternoon, all. I'm Raviraj. I do work under supervision of Professor Arindam Chakravarti. Today, we are here to discuss machine learning for monsoon forecasting. We will basically address this. We'll look at these four topics or questions, you can say, like what are neural networks or deep learning? How are they useful to climate science or in a specific case of the monsoon forecast? Uh, then there are few generalization problems with uh, typically known in the field of deep learning, like rare events and climate change, specifically for our field. Can we incorporate climate change in these particular models and help get a generalizable forecast? These questions will look at in the presentation. So first one, let's have a quick look at what are neural networks or deep learning. These days, artificial intelligence is short form as AI, machine learning, and deep learning are quite used term a lot, like day to day life in a day to day life. So artificial intelligence is basically machines who specifically uh, task for having a simulation which mimics the human behavior and can perform a task which usually we humans do. Which is a superset of deep learning and machine learning. Under this subset of AI comes deep learning, where we specifically learn from data with the help of statistical techniques. Basically, machines learn from data with the help of statistical techniques without human intervention. And deep learning comes under this superset of machine learning, where specifically we take help of artificial neural networks, where the neural network, the word neural is inspired from the how brain in the human, basically how the human brain works, and these artificial neural networks are based on, inspired by the function of neurons in the brain. We'll have a look at deep learning specifically. So deep learning or neural networks, quite terms used for the same methodology basically. So neural networks are flexible functions which can help us to which can help us to have a flexible function which fits between the input data, which is represented over here by x, and y hat is a approximate output derived from this particular input, where theta are learnable parameters which we learn throughout the training. So this particular diagram, each and every circle is represented by called as a node or neuron, and it simply performs this kind of mathematical operation where input x goes and has a linear relationship like this w1 x plus b1 within from one neuron to another neuron in the next layer. So this linear relationship gets transformed, or again a nonlinear function sigma gets applied over that linear relationship. And this kind of operation follows throughout the neural network as it goes right on the right side or towards the output. So theta are basically called weights and bias. And those, as I said, those are the learnable parameters in the neural network. We are supposed to learn those, and by learning those, we will have a good fit between output and input. So this is a a very easy example of polynomial fitting. Basically, with the noisy data, training data, we try to fit a good looking curve, a polynomial curve, which is a approximate representation of the actual polynomial function. So what I want you guys to take from this particular presentation is this will be the most important slide, and this can be taken as a take home message where whenever you heard neural networks or deep learning, any neural network or deep learning model is doing this particular work only, like fitting a flexible function, fitting an approximate function which represents a relationship between some input data and some output data. So how do we train this? So we looked at this NN, capital NN represents neural network function, and it gets inputs xi and theta, the trainable parameters. Here y subscript I represents the actual output, and we do the mean square error calculation of that particular this particular term, and this represents the how far we are from the actual function, and that is considered as a loss residual. We do want to optimize it to the minima as it is shown in this curve. This is a 1D curve, but in actual training, this theta will be the millions of parameters. So this curve will not be this simple looking, and it will have multi dimensions. But ultimately, goal is to minimize that particular loss and get us a W or theta that are learnable parameters such that we will get the minimized loss, and we'll have good approximation fit between inputs and outputs. And once trained, neural network gets are saved, and during test, we just have to pass the input data. We'll get the output as a prediction of our model. So how we have been using, or how our community have been using this in climate science or monsoon forecast, we will quickly have a look at few examples. So this is a convolution neural network, which takes in general, convolution neural network takes images as an input, and as we might know, like color image as a 3D array of red, green, and blue colors. And this matrix basically represents some numbers. Dominance of one particular number will, dominance of any particular number will decide which color we'll get as output. So we all might have gone through this El Nino and La Nina event at least sometime. And we know that when we see in any SST map, when we see red color towards the East Equatorial Pacific, we call it as El Nino year, or West Equatorial Pacific. Similarly, if we see that bright red color in the West Equatorial Pacific in SST map, sorry, this is not actual SST map, but when we see red color on the west side, we call it as a La Nina year. So we do this manually as a pattern recognition from the SST map. The neural network, or specifically convolution neural networks, are very good at predicting the patterns from images. And so we'll have one example. This is a particular paper called Deep Learning for Multi-Year Enso Forecast, where it takes SST and heat content. Heat content is basically vertically average oceanic temperature up to 300-meter depth from the surface. So three previous months SST maps are provided as images to the input to the convolution neural network. This is the input panel, SST and heat content. And we get output as a M34 index for succeeding or upcoming from month tau plus 1, like next month, to lead time of 23 months, we get the M34 index. In between, there are a few other terminologies. We can specifically have a look at this convolution layer, which is called convolution layer because it has some filters called convolution filters, which are kind of matrix with weighted values given as an input. And when these convolution filters convolve or slides over each and every input image, it specifically learns patterns from the image and helps us to get to the output. So this particular study had good prediction for N34 up to lead time of more than half a year. So this is a skill comparison where all others are conventional models, and this particular top line, as we can see, after a lead time of 6 months, the x-axis is the forecast lead. After lead time of 6 months, correlation scale of this particular CNN model, convolution neural network models, dominates or outperforms all other conventional models till Even 17 months lead time, it is having skill greater than 0.5, which is very interesting.
Raviraj, we discussed paper 2 years ago. It's a very good paper, but this person has not made real-time forecast yet. Have you seen any? Because this paper is very good. He made a forecast with the one. This is essentially analysis of past data. But in real time, I would like to see how this model is done for last year and this year. Have you seen any?
Not like that.
Yeah, look at it, because he has done good work, but I didn't see any follow-up. This is 6 years old. So
Yeah.
by now I should have predicted many El Nino, La Nina, or non-occurrence and so on. But I looked around, I couldn't find any paper. So it's worth exploring who else has cited this paper and what further work is done last 6 years. That paper was very good, very impressive.
Sure.
So he should have forecast last year, no El Nino, La Nina, and year before, but I didn't see any papers.
Yeah.
Okay.
Even I haven't come across that. So this is another example for monsoon prediction, autoencoder. Autoencoder basically learns, basically compresses input data and takes it into the latent space, where we will remove the noise from the data and restructure it to get the whatever input information we are having within just with the latent or potent data from that particular input data. This is kind of dimensionality reduction technique. So this was particularly for discovery of monsoon predictors. This particular paper is from Momita Shah, and Professor Ravi is also co-author. So this was for data discovery or knowledge discovery. Like one part of the model does gets us to the new monsoon predictors, and once we get the new monsoon predictors, that particular predictors are passed to the again nonlinear model, kind of deep learning model itself, to get the forecast for the seasonal monsoon anomaly. So yeah, input for these were again like air temperature, SST, and SLP. Through this, they pass, as I said, global data, and out of that global data, we get important regions which have connection to the monsoon in the first stage of knowledge discovery. And this, in the second stage, it help that particular predictors help us to predict the seasonal prediction of monsoon. Let's have a look at what was the skill or how was the prediction. So these are the test years, and this is a percentage anomaly for seasonal rainfall. So skill was impressively greater than 0.7, and we can see that this is a purple line is actual, and the last one hatched line is the deep learning autoencoders prediction with air temperature, just with air temperature, and other are IMD forecast. So many years like this, 2003 or 2012, we get a good prediction with this particular autoencoder model, and no, it can be considered like errors were also quite impressive and less than IMD's forecast. But in this particular forecast, I want to grab your attention to the thing that when year 2009 came, which was having a severe drought, percentage anomaly was way below than -20%. This model or even IMD forecast was not able to capture the magnitude even in this year. So whenever we are having a anomaly which is deviating from the climatology much more than 10%, it is not getting that particular magnitude getting captured correctly with this model. And this issue persists with many other models or any in general model of such sort. We will have a look at those things also in coming few slides. Test period for this. Sorry. Test period. I think it was some 30 years. 1970. So it was approximately, I think, 25 to 30 years test period before this 2002. I think. Not exactly able to recall. get to this particular thing later. So there are other global data-driven models also, like ForecastNet, Pongu, GraphCast, many and many others. We might have come across all these, at least names we might have heard. So what these global models do are they take training data from ERA 5 reanalysis data as a training data, and they do a short to medium range prediction on 0.25-degree resolution, which is quite impressive. Uh, like they do forecast for high resolution variables like surface wind speed, precipitation, atmospheric water vapor, and skill or accuracy of these models is comparable to integrated forecast system of ECMWF at short lead times for large scale variables. But interestingly, they outperform IFS for small scale variables. And this is an important point about all these global models. Like they can do a small scale variables prediction much faster and at a better accuracy than the conventional dynamic models. And even once they train, after that, within a fraction of seconds or within a couple of minutes, they are able to generate forecasts for many uh, forecasts with many ensembles, which can improve the probabilistic forecast. So as we discussed just with this slide, there was a problem with years which have a much larger magnitude of anomaly. And we'll have a quick look at some other particular models which also have similar events. Like if there are rare events, or even in the case of climate change, climate warming, we will get those particular generalization issue with these models. So this is again a generalization problem in one of the shown in one of the papers, where they wanted to forecast for the strong tropical cyclones. So in this particular block, like low MSLP obviously represents stronger tropical cyclones. What they did is once they passed all training data, including stronger tropical cyclones, in a second case they removed 25% of training data in general, and in the third case they have removed 25% training, like all those tropical cyclones which are which have like, lowest 25% of the data which has the category 3 to 5 tropical cyclones. So when once we remove these particular strong tropical cyclones from the training data itself, getting them predicted is a little difficult, as we can see on the right hand side. Like with this particular all training data, this black line is obviously ERA 5 observed, and the prediction also follows that particular dip, like drop in the MSLP quite correctly. In the second case also it follows. But in the third case, where we have removed the stronger tropical cyclones, 25% data with stronger tropical cyclones, this does not show that trend of MSLP dropping with that particular event of one particular event of cyclone. So this is again a kind of generalization issue we see. This was a good test problem where they removed the kind of extreme events or rare events from the training data, and we could not like model could not catch that particular uh, cyclone properly. Similar to this, there is again a study paper source as climate invariant machine learning, where we have a cold climate. They particularly took this data from super parameterized community atmosphere model version 3 and super parameter community earth system model version 2. So in these cases, they generated data for -4 from the Kelvin from the reference climate, and also in the warm climate they referred warm climate for +4 like Kelvin temperature from the reference climate. And when they conducted a test, the models do perform when they trained on the cold climate, and if they test on the cold climate itself, they do perform better. But when they trained on the cold climate and the test happened on the warm climate, the performance was poor. This is again a generalization problem we quite a lot see in this kind of models. So this particular paper had tried to incorporate these kind of issues, specifically the climate change issue. We will have a look at it. So this was a study to develop a machine learning model to capture subgrid processes, and input data was provided from these particular dynamic models, super parameter dynamic models. Input was a large scale variables like specific humidity, temperature, vertical profile of specific humidity, temperature, then surface latent heat, surface sensible heat flux, surface latent heat flux, or surface pressure, all those sort. And in the output, they captured thermodynamic tendency resolved for the subgrid processes. So, tendency for specific humidity, temperature, long wave heating, and short wave heating was the outputs from this particular model. And interestingly, for all these capturing all these subgrid processes, they took help of physical transformation based on thermodynamics and incorporated this knowledge in the like before the learning process itself. So it can be called as a physics guided neural networks. We'll have a look at this, how they did these physical transformations or incorporating knowledge of climate processes. So the raw data over here represents the uh, data from different climates, where warm climate is represented by red line and cold is by blue line. And raw in outputs are represented over in the above panel. So the aim was to physically transform these, like these are the PDF profiles. Aim was to physically transform this PDF profile such that after transforming, we will get a climate invariant data, which is represented over the below panel. Like this latent heat flux was represented, transformed with some quantity referred as LHF subscript delta Q. Then temperature was transformed to the buoyancy claims, and specific humidity transformed to the relative humidity. We all can observe that there was a discrepancy or there was a difference in these PDF profiles in the raw data, but these profiles are somewhat climate invariant, as they call, like they are not dependent on whether it is data is from cold climate or warm climate. Similarly, there was a process to transform outputs also. Once they are transformed, they pass this data in the deep learning model, which could help to predict us better whether data coming from warm climate or cold climate, that doesn't matter. Prediction was comparable in the both the cases. So this is a particular, I'm explaining just one particular parameter, how they transform specific humidity into relative humidity. Similar transformations was happened for others. So these are the raw data for specific humidity. We see that the red curve, which is a warm climate, and the gray is a reference, and cold is a blue. With the climate warming in the both models, we see that the variance of the data with warm climate is way higher. PDF gets distributed over a longer range with the climate warming. So they transform this specific humidity to the relative humidity, where it's a ratio of partial pressure of water to its saturation value. As we know from the Clausius-Capron relation, that saturation value also gets exponentially increased with temperature. So dividing this particular saturation value kind of gets the warm PDF distribution gets again aligned, or gets basically warm and cold climates PDF distributions are overlapping in this particular transformation, where they did it from the specific humidity to relative humidity. Similar transformations was done for other particular inputs and also for the outputs. So with this transformation, when we look at the panel A, this is basically comparison of mean square error when model was trained and tested. So mean square error, this is for cold climate, and this is for generalization test for warm climate. So all are the output profiles for mean square error, like humidity, specific humidity, tendency for specific humidity, tendency for temperature, and maybe long wave heating, short wave heating. On the left hand side, when we see that like this blue is a raw data for the cold climate, and then orange one is that once specific humidity gets transformed, then green is this was a gradual transformation. The green is transformation of specific humidity along with temperature, and the last one bright red is a transformation of specific humidity, temperature, and latent heat flux. When all these all three gets gradually transformed, and when it training was happened in the cold climate and testing was also happened in the cold climate, we see all the profiles are overlapping with each other, which shows that this transformation doesn't matter when we are testing for cold to cold only. But when we are going to transform this, when we are going to test this particular model based on training in the cold tropics, but testing happens in the warm tropics, we see that raw data, which is blue line, which has the largest mean square error. This is just the zoomed view for this particular figure. Same happens for these particular figures. So the blue line, which is the test in the warm tropics based on the training in the cold tropics, which is having the largest mean square error in each and every output variable. But as we get gradually transformed from orange, green to red, these mean square error profiles values gets dropped and they get close to the like these values are getting reduced, and this particular purple line is basically test of this model in the based on the data training from the warm tropics and test also in the warm tropics. That's how the purple line shows the lowest mean square error in each and every profile. So we can easily see that these transformation lines like orange and up to the red gets gradually mean square error gets gradually decrement at each and every output of the model. So again, one particular result from the paper where they predicted for 500 hectopascal subgrid heating, and this particular upper panel shows coefficient of determination when model was trained on the cold tropics and tested in the warm climate. The tropics particularly shows very poor prediction or very less coefficient of determination. But when they tested on into the climate invariant model, so this was the raw data mapping without climate invariant. But when they turned into the climate invariant model, training it on the cold climate and testing it on the warm climate gives a better result compared to when it was done on the raw data. So even in the tropics, you can see that better generalization or better prediction for subgrade heating. In conclusion, we can say that ML techniques can provide better forecast, but most of the times they fail to generalize for rare events or in different climate or configurations of models. Particularly if these rare events and these climates were not taken into consideration while training, they will definitely fail to generalize. So it is recommended to train ML models based on multiple climates, and incorporating physical knowledge into ML models can definitely help to improve their consistency and generalizability across the climates. Thank you. Yeah, I'm open for questions.
Thank you. Yeah, the monsoon is going along smoothly. As you can see, we are now 10% above normal, cumulative. And in July, half of July lowered, still 11% above normal. But of course, the difference between northwest, central, and south and east is significant. That is not changing. Okay? So this is a particular pattern we are following this year, which I will mention very soon. So if you look at a spatial pattern, this is the feature this year. Rain is supposed to be hanging around the this region with less rainfall in the foothills and in south and northeast. Okay. Now, this is the pattern. If you did EOF analysis of India's rainfall in July and August, not June and September, those are a little more tricky. So July and August, we do EOF. There's a clear, this pattern is visible. Okay. For 22% of the time. So this pattern is to be expected in the month of July and August. Now, if you look at the time series, you can see that after about June 15, except for 1 or 2 weeks, so not 2 days rather, rainfall is above normal in whole of India. But if you take only the monsoon zone, okay, this is the time series for all the 4 regions. Again, you can see this and this are the division. These two are doing well. But if you look at the monsoon core, it is more easy to interpret, and all the analysis done only for the monsoon core, and you show everything in terms of standardized rainfall. Okay, subtract the mean and divide by sigma. You can see that unique thing about this July is July 1st is somewhere here. From there are 1, 2, 3, 4, 5, 6, 7, 8 days in a 16-day period when you're above 1 sigma. Okay, this is what Rajivan in his paper published in just calls it active days. Okay, so we already had 8 active days in July, and this is very unusual. Okay, not common. So the expectation is if there is so many active days in just 15 days, will our rainfall be above normal at the end of the season? It's not so simple. So if you look at Rajivan's paper, they plot the seasonal mean departure of rainfall with number of active days, defined as days in which the core monsoon core zone is above 1 sigma. Okay, you can see that up to 10 days, distribution is uniform. You can't predict anything. Why? Because things are going well. It will go on for some more time. There's a pretty good chance August will have a long break like in 23. Okay, you cannot rule it out. So, but what's interesting is you go beyond 10, then there are 4 years where once again beyond 10 gave very good rainfall, but exceptional 2006. In spite of having 23 active days, it was normal. Okay. So what's interesting is that active days, that is there, do not guarantee if you have more active days, there is a higher rainfall. Up to around 12 days, it's distributed equally. Slight deviation that side, but there's always an exception. So this is a warning that we cannot easily predict the future in the case of the monsoon. Okay, now let me give a few examples of how well the model is done in short-term forecasting. This is prediction for 8 July based on 7 July. And you can see that this is the GFS model. This is the observation. I should normally to highlight the high rainfall. Now this agrees more or less with this. Okay. So that I would say not surprising. 1 day forecast of all is usually good. Next one is for July 15th, 2-day forecast, okay, from based on 13th. And I would say here also, these 2 features are well captured. Even that one is okay. So again, short-term forecast, this is ECMWF. They are doing quite well. Next one is I'm comparing, we did it last week, I'm repeating it. What is the forecast for the 30th of July based on 10th of July, 3 days ahead? And you saw a difference between ECMWF and GFS. The difference was right here. Okay. Close to Gujarat here, ECMWF had very high rainfall. This did not. Okay. Let's see the actual data. I would say ECMWF has done better. This is where the high rainfall occurred, and these 2 were captured with both. But this feature, GFS did not have either this or this. So for some reason, we have seen this the last few weeks, some reason GFS tends to not to give good rainfall over Rajasthan, Pakistan region. So I'm curious why. It's what, because this is a systematic error. This is not just one off. We have seen it now 4 or 5 times. And I've looked at the African rainfall where many models get a wrong result because they give the wrong albedo of the surface. Surface albedo is a very critical parameter in regions like Pakistan, Rajasthan, and Africa. So I would like someone to look at what kind of albedo have they given and how close it is to the observed albedo. Today, because you have satellite data, we can get very accurate albedo of the ground on clear days. And that has to be incorporated in the model. I think it's not being done. Okay, there's another example from GFS, from the IMD website. The reason I'm showing you is, again, a one-day forecast, is that the rainfall, what do you call, even here is oriented at an angle. Here is almost like an ITC. So it's got something wrong. And to me, that is should worry them, because one-day forecast should be very good. Because even all the initial data you have done assimilation, you should be very good. So this to me is a cause of concern why they couldn't get this pattern. They get sort of part of it, but don't get the coherence that observation shows. Okay? So this one example, there we have failed. Here's one more. This is 9th July initial condition prediction for 10th one-day forecast. Again, I would say it's extremely good. Whole line correctly predicts this. Okay. So all the one-day forecasts are showing the right spatial pattern. Okay. This one is again 10th July for 11th July, and I would say more or less similar pattern. Now let's look at weekly mean last week. That also is good. This is the forecast. This is the observation. It is the entire region here was correctly forecast. This was correctly forecast. This was correctly forecast. Slight difference here. And again, mistake over Kerala. Because orographic rain, there are problems in many models. Okay. Here, there is a slight difference. Otherwise, monsoon core zone, they got it, the weekly mean almost correctly. Okay. To be precise, they predicted 31% above normal. Actual was 26, which I would say is, yeah.
Prediction is done using the IMD's model.
Yeah, this is all IMD. This is the IMD forecast, this is the IMD observation. Both are IMD.
This is the 12 kilometer from ECM, the LCM W. This prediction?
This prediction is IMD, that is GFS. They use GFS model.
Okay, that is different from what national
Yeah.
forecast.
Yeah, that is American GFS, this is the Indian GFS. Slight difference is there in resolution and so on. Now, we look at the why we have been having this persistent rainfall over North India for the last 15 days. You look at the velocity anomaly on a given day, you can see that this entire region is having ascending motion. This entire region having descending motion. And this pattern is quite common in July and August, okay? And even in September. But June, you won't see this. June is very different. June is the onset phase of monsoon. If you look at the June velocity potential, you will see there will be 2 rising motions and 2 sinking motions. Okay? I have never seen anyone explain that. It's worth looking at why the June circulation pattern in the tropics is different from July, August, September. So I thought June and September will be same, and July, August being the peak monsoon, it will have a large spatial effect. But September follows July and August. So this is a puzzle which needs to be looked at. Now let's look at the all India monsoon rainfall. And although there are errors from day to day, overall correctly predicts the weekly of the monsoon. Okay, this trend was correctly predicted 10 days in advance. So I would say that is a good thing about GFS. Now, this year is unique because there is hardly any El Nino, La Nina phenomena, or even IOD. Okay, so this year's monsoon has been driven by this. Look at the anomaly here, 1 to 2.5 degrees. This is what is driving it. But I have not seen anyone do analysis when only this is there and the rest is not so good. Now, let's say why the model are not doing so well. See, the IMD's forecast or the coupled model says July will be a La Nina. All of you know it's not La Nina. You can look at the data from Australian forecast, it is 0. Okay. So the coupled model got the forecast of 3.4 wrong. Okay. That is for the El Nino region. Now you go to the IOD region, the forecast for June and July and August is highly negative. Okay. IOD. If IOD had really been negative, it would have had some association with rainfall. But in reality, IOD is close to 0. Okay. So they got both of them wrong, both Indian Ocean and the Pacific Ocean. The coupled model has problems still. We know that problems still exist. Okay. Now we go to forecast for the coming week. Now this is a forecast from NSEP GFS, and this shows this continuation of this pattern till the 19th of July, that is end of this week. So this is continue, and this is also get high rainfall. So this is the prediction of NSEP. Okay. Now, what's the forecast for all India rainfall? It shows slight increase and then a decrease. So essentially, most of the coming 10 days is weak, below normal. 1 or 2 days, it might be more active. Most is below normal. So this is the weakening trend of the monsoon after a good 15 days in July. Okay. Now, this is the spatial pattern of the forecast. You can see clearly this week, this will continue. This will weaken. Actually shown there, okay? And south will strengthen. That is the forecast for the next week here, which we'll discuss later. Now, this is the comparison between GFS and ECMWF. And once more, the same tendency. GFS tends to predict too much of below normal rainfall in this region, while it does not. And ECMWF predicts much more higher rainfall also normally here than here. So there's a difference, and I think most of the time ECMWF will be right. We'll check this 2 weeks later. Now, this is the more detailed discussion of the ECMWF forecast. Again, this unusual pattern which goes right across to Japan, okay? Followed by this below normal rainfall. So this pattern, which is these were connected, the very what you call large scale pattern, which is easier to predict by any model. This is next week, 21st July to 28th July. You go to 28th to the 4th August. Now comes the problem. Slowly the below normal rainfall starts moving up. This starts weakening. Okay. So by the time August comes, you will see the situation will get worse. And that's the forecast of ECMWF. As you come to the first week of August, you can see the whole band of below normal rainfall is here. And this is pretty much almost gone. This one, okay. And let's say the next week, although 4 weeks ahead, I'm not sure how good the forecast is, but this is the warning. So according to ECMWF, by the time we come to the 11th of August week, pretty much India will be having a sort of break period. Okay. So this keep in mind, we'll discuss that whether that actually happens, because all of us know that the first 2 weeks is good and then it deteriorates rapidly. But some of ECMWF is usually doing better. So we'll keep an eye on this forecast 2 weeks from now. Okay. Now, what is the forecast for August? There's a monthly forecast available in the GFS website of US, and it says slightly above normal, interestingly, and well above normal in the West Pacific. But what I'm interested in this particular feature, I don't know what it is. If any of you have seen it, you should tell me that just hugging the coast of India, there's a sharp difference in the anomaly. And there has to be understanding. I don't know what will explain this sharp thing which goes all the way to Myanmar, Sri Lanka, this one, and this has have a dynamical reason. But right now, I'm not able to see, and I have to see what forecast Eastern Development gave for this period. Let me see whether I can get out of that. They normally don't give monthly means. Okay, that's a brief thing about Karnataka. Now and then we'll have to look at rainfall on Karnataka. See, June rainfall is normally around in South Indian Karnataka, which covers Bangalore, is around 65 millimeters. Okay, that's a normal. So it was good in 21, 22 was very good, 23 was slightly below, but this year is the lowest in this series. Okay, and but what I want you to highlight here is the difference between South Indian Karnataka and Malnad region. Malnad region is just the lee side of the Western Ghats. Okay, so they tend to be opposite. They're one of them is opposite here. This is outer phase and this is outer phase. Only 1 year they were all having the this is also outer phase here. Yeah, only 1 year, that is 23. All of Karnataka are the same. There's some large scale phenomena. Okay, and the large phenomenon involved, the whole of Karnataka is below normal. But in most years, you can see there's automatic relationship, which I don't have a clear understanding, because I had a simple view that Western Ghats is here. If it rains every year, it will not rain much here in Malnad, but we are well away, Bangalore, from the Western Ghats. So I don't know what the connection is, but so this outer phase relation is interesting. It is some local feature which needs to be examined. Now I learned with a very interesting, I'm not a believer in social media. I don't use TikTok. I don't use WhatsApp. I hate them because they are very disruptive. Okay? I only check with email, nothing else. I found this interesting preprint from IT Bombay. Okay? They have put a time series of the crowdsourced data of the Twitter number of tweets in Mumbai in 2017 from June to 22 September. Okay, and they are arguing that tweets and the rainfall are very close to each other. Well, it's not a surprising part. If there's more rain, people are tweeting each other about rain. So that's obvious. The implication here is that someone can use tweet to predict rainfall. I don't think you can do that. I'll tell you why. All of you in the era of machine learning data science, you must be very careful about any data you see. In this data, they are not giving all the days. They are given only days where there were extreme rainfall. Okay, then naturally the tweets go up. But it's interesting, there is a pretty good correlation between high rain and high tweets, and not so high rain. Remember, there is 100 millimeters rain. Mumbai, it rains a lot. Okay? So even 50 millimeters, so there is some connection, but I don't think it's very useful, because if you put all the days, not just these days, there will be days with high tweets when there's no rain, because there's an Akash, Ahmedabad, or something else somewhere. So unless, I don't know, I'm not exposed to media, if the tweet has the word rain and you use it, maybe it will be good. Otherwise, I don't see. But it's interesting data. And today, all of you use social media. Maybe you can see whether you can see some interesting pattern in Bangalore, similar to Mumbai. Okay, thank you. Now, yeah. Huh?
On this front,
Right.
data, we looked into Google Trends.
Huh?
Google Trend.
Okay.
So in the Google Trend, we were looking for dengue
Okay.
in Bangalore.
Huh.
So when you read that search, actually we got a very good correlation between what happens on the ground versus what has been people have searched. So there is a good correlation. Yeah. But you cannot use for prediction.
But what would you say? Tweeting between the various reasons.
Yeah.
So tell me, when a complete tweet and the word rain is there, it can be captured.
I don't know. We looked into the Google Trend data.
Okay.
So for a dengue prediction. So that had a nice correlation.
Yeah, yeah. Actually, the Google is using it to predict traffic, so that's value to it. Actually, the most valuable physics-based method was done in Israel more than 10 years back, which is based on all your mobile, this one, the signal beacons will rain. It can be used for direct estimate of rainfall. I don't know why we are not using it only because I think I asked somebody in India, our great people who own the mobile business, they don't share data. If you can get the data from Geo and everybody else, you can predict in real time rainfall because between two towers there is rapid integration of signal. That is very valuable for urban areas. So I'm sure there are 100 towers in Bangalore, right?
More than.
But if some of you smart are able to deal with the company and get the data, even not in real time, but now with the past data, to demonstrate what Israel did 10 years ago, and on the nature paper, which is very nice. But I'm not seeing any progress in India on that. So that is not
Someone else, you guys was doing this.
really.
Yeah, I forgot the students then. I think
Okay.
you just couldn't do anything.
Yeah, somebody got very talk in this forum, I don't know.
Yeah.
They did. But I think it's because unless you get an actual data from the company, you cannot do much.
So this meeting is about rainfall, we did about everything.
I think about rainfall, yeah.
So that is very natural. It's a
In fact,
Maybe it's interesting. That's the reason. In a country where you don't get real time data from the government, it's good to look at especially for extreme rain. This will be quite useful for the people because it will come in their real time, right?
understand.
So it's valuable.
Yeah, just on a, I mean, as a human, that if we do not have some many places, we don't have rainy day, right?
Yeah.
So we can.
Yeah. Yeah. The very good point, the lot of possibilities is no engage, so the quick you get indirectly. Albeit, it is very important to identify. Indian government, if I remember correctly, the exact number I don't know, but close to lakh crore in insurance for agriculture. Okay? Very lot of money because farmers are big voting lobby. Now, the trouble is that there are areas of India where there is not enough drainage. The farmer says, I have a drought. How do you verify? Maybe it will help.
Yeah.
It's a very important point. Yeah. Okay, so next week there is no volunteers, so we are not meeting next week, we are afraid. We'll meet on 30th July. Who is on 30th?
Next week, Ritesh.
Ritesh,
Ritesh.
agreed?
Yeah, please.
I didn't communicate, okay, Ritesh, okay, that's good. Now, I was not sure, I thought we will do it. It already was good. Now they are in the list, or not already.
In the list. I think I will share. I have shown.
Okay, thank you, next weekend.